show some properties of such nanoporous materials. Here on the left side, you see a nanoporous material. It's gold. This was produced by leaching out the silver of a gold-silver alloy. And here, the black parts are the pores, and the white part is the gold. So you see there's a network of gold crystals interconnected, and in between are the pores. Now we take that thing, dip it into electrolyte, in this case KOH, and then we have a situation like that. And then we apply a voltage between the gold and the electrolyte, and therefore we get all these interfaces. We have this very high charge at these interfaces. And that dramatically changes the properties. I'll show you three examples. One is here. This is here the magnetic moment as a function of the applied voltage. So the applied voltage between the electrolyte and the material, and in this case it was a palladium-nickel nanoporous materials, is about plus minus 0.5 volts. So a very small voltage is applied, and you can see that the magnetic moment goes up by 45%. So magnetically, that changes very dramatically by just applying plus minus 0.5 volts. A similar effect here. It's a ceramic material, ITO, and we produce it as a nanoporous material, apply a voltage of about plus minus 0.2 volts, again a very small voltage, and you can see that the electrical resistivity changes even by 300%. It's clear why it changes so rapidly, because you have very few carrier-free charge carriers, and if you pull a lot of charge carriers out, it's no surprise that the resistivity goes way up and down. And here is an example from Sendai, the superconductivity in nanoporous strontium titanium dioxide. This material is normally an insulator, but when you produce it as a nanoporous materials and you charge the surface, in this case it was potassium ions which were deposited, then the charge is so high that the strontium titanate becomes a superconductor. And here you can see the resistivity as a function of temperature, and here you see the thing becomes a superconductor at about 0.4 Kelvin. Again, these are just a few measurements that were carried out. There's a whole world of new effects of these nanoporous materials, essentially by, again, just going a little bit away from what has been done so far, not electrically neutral, go to electrically non-neutral materials. Charge and discharge coupling, I think. Now, one can go one step further. These are three-dimensional systems. Of course, for molecular electronics, an interesting case would be a one-dimensional system of that type. And we tried to do that, and we again saw new effects.